Hi and good afternoon, everybody. Welcome to this webinar on steel connection design. My name is Andras Herbay. I'm a sales manager here at the MasterSeries. As usual, I'm joined by my colleague, Patrick McGinley. Before I start the presentation, I would like to quickly share some practical information about the GoToWebinar. So the control panel can be hidden with a red arrow button. Questions or messages can be sent with the chat option. Feel free to type in your questions at any time during the webinar. We will answer them during the session, but we will also review the questions at the end of the webinar. As usual, this webinar is being recorded and will be posted to our channels and sent out to your email address. Few words about the agenda. First, Patrick will give an overview of the different connection types we can design using the MasterSeries. After that, I will demonstrate how easy it is to design and optimize a steel connection using the connection design software. During my presentation, I will also present how a connection can be auto-designed. I will speak a bit about how you can use the joint template library to standardize and optimize your connection design workflow. And after that, I will quickly review the latest major developments in the connection design module. And as usual, we will finish with a QA section. Okay, and now let me hand over the presentation to Patrick.
Okay, so today I'll be going through a 3D model, basically to show the different types of connections available within the MasterSeries connection design module. They help give you an idea of what can be achieved within the software and including any limitations as well. So I'll talk about mostly the practical considerations when specifying these connections and things to look out for or consider depending on the type of connection you are specifying. And I generally won't get into any detailed numbers on the design, for example. So I'll be using a third-party software application, in this case SketchUp, for presentation purposes only. So just a caveat that the 3D model I'm using is not in MasterFrame, nor is it a perfect analytical model either. So it's purely for presentation purposes. And I'm using a single-story steel frame for this example, as it covers most of the types of connections available in the software. But be aware that these connections can be used for multiple building types and frame types, from single-story to multi-story buildings, and many of these connections can be used for steel truss connections as well. The connection designs in MasterSeries are in line with the UK best practice guidance as presented in the SCA Green Book publications you might be familiar with. So that covers the design of simple connections based on a shear force only design force due to loading in the major axis, and moment connection designs include major axis moment and shear due to major axis loading, and then axial forces as well in compression and tension. And moments and shears due to minor axis loading are not considered in line with the design methodology of the Green Books, except for when we are looking at splice connections. We'll cover that. I'd also recommend referencing our manual as well. Maybe pull it up, as it will provide relevant information and knowledge relating to all the different connection types we have in the software. And as always, we're keen to hear your engagement and questions in the chat box. So starting out with simple connections. So simple connections are almost always cheaper to fabricate than moment resistant connections because they involve much less fabrication effort, particularly in welding. So the material cost for fitting and bolts is small compared with workmanship costs, which are dominated by welding. And in a typical fabrication workshop, the cost of fabrication of connections may be up to 30 to 50% of the total fabrication cost. And when you compare that, typical braced multi-story building, bracing accounts for about 5% of the weight on average, which is not really correlated with 30% of the costs, or 50% in cases. So first connection we're looking at is a beam-to-beam flexible M-plate connection. So usually in beam-to-beam connections, the supported beam is notched to keep the top flange flush with the supporting beam, and the end plate, either partial depth or full depth, is welded to the supported beam in the workshop and then bolted to the supporting beam on site or column as well. So the flexible end plate is typically the strongest of the three simple connection types I'll be going through today, but there are some basic differences in full and partial end plates. So fully will be extended on down to cover the flanges, bottom and top flanges there. So for shear resistance, you can get up to 75% of beam shear resistance for partial depth end plate and up to 100% for full depth end plates. And then for tying resistance, we're relying a lot on the weld and the capacity of the end plate to transfer the loads between the bolts and the web of the supported beam. So you may require a thicker end plate there. Tying resistance is stronger when using a full depth end plate, as the flanges will also be welded. Full depth end plates are also slightly better for temporary stability. Overall, the flexible end plates are relatively inexpensive, and they're often used to connect primary beams to columns as well. And we can use packs to use for compensate for fabrication tolerances and erection tolerances. Probably the most popular of the simple beam connections currently in use in the UK and can tolerate moderate offsets in beam to column joint. So I could just jump over to what they look like on a column connection there as well. So same principle, welded onto the supported beam and then bolted onto the column there. We now have in 2023 the option to specify toe plates, and they're popular for solving the installation of these beams because you're avoiding to have to notch the beams on the top flange, for example, and it can be easier for erectors as it eliminates the problem of swinging in your beams and trying to get that the web to fit in there. So it's preferred in that regard, but these connections are expensive and they use a lot more material. So from a cost and sustainability standpoint, they're not ideal to be over specified. The use of toe plates is common practice in the UK industry, and although there is no official guidance on how best to approach the topic, our MasterSeries director, Dr. Martin O'Gara, has developed a technical note on the topic, which does a bit of a deep dive with some finite element analysis carried out to show the behaviour of these type of connections and what critical factors are at play. So giving an explanation of how the supported and supporting beam interact. So this will help users who specify the end plate connection understand the design considerations and how we can either specify a simple or moment connection design approach within the software. Ultimately, let me see, I'll try and pull that up here, that technical note. So yep, so it's about 10 pages there, but you can have a look through it. We have uploaded it onto the handouts here on GoToWebinar, so you can download it from there. Ultimately, it is the engineer's responsibility to choose the appropriate design approach. So it's recommended when specifying this type of connection that the designer understand the factors involved. So we've attached as a handout there the technical note, and for future listeners, we will leave a link to the note when we post this video to our social media channels. Andras will also talk through this as well and provide some templates for the toe plate connections. So our next connection type is fin plate connections. So that consists of a length of plate welded in the workshop to the supporting member, to which the supported beam is bolted on site, as we can see in the figure there. Thin plate connections are economical to fabricate and simple to erect. They're often used to connect secondary beams to primary beams or to columns. And these connections are popular as they can be the quickest connection to erect and overcome the problem of shared bolts in two-sided connections. So we're just bolting through this supported beam rather than sometimes a larger supporting beam or column. And then as well, you can usually get around a third of the bolts in, and then you can allow the connection to hold the self-weight of the beam while you unhook the crane on site. So that's popular for that reason as well. It accommodates skewed and raking beams, plus offsets can easily be accommodated as well. They have a high tiring resistance and compared to the partial end plate example before, as there's a more direct load path and you're not having to rely on the bending of the end plate as you would be on the flexible end plate. So this is beneficial for higher class buildings for disproportionate collapse as well. So it can be difficult to fit in narrow columns, so it may require cutting of the flanges locally to accommodate that. So worth noting, I think that is also considered within the software as well. So you'll be able to see that when you specify that in the connections designer. Lastly, we have our double angle web cleats. These are currently not as popular as the equivalent end plate connections for a few reasons. That will be because it requires bolts in both directions, and you are it's maybe a bit more cumbersome, restrictive to its welded equivalents, and it's unsuitable for skew connections as the angles are just at right angles. But it does offer advantages in that it does avoid any welding, and so it's the best connection in terms of opportunity for adjusting on site, as the two sets of bolts allow for adjustments in both directions before they're tightened. Also, it offers the advantage of having a fully demountable connection at the end of life with no welded plates. So with the push in sustainability issues, we could see that increase in popularity over the coming years. In design, it is similar to the thin plate as it is limited in shear capacity due to the reliance on bolts, but good in tying, as again, there's no reliance on the bending of end plates for load transfer. For all these simple connection types, I'll just jump to the column image as I have it done anyway. But for all the simple connection types, it's typically better to have the plate located closer to the top flange. That will help provide positional restraint to the supported beam. Now, next, we'll look at a simple base plate. The software can design base plates for columns of open eye sections and rectangular, square, or circular hollow sections. And just some normal practice in the UK, holding down bolts are cast in place with an arrangement of 4 bolts as a minimum, irrespective of whether the base is assumed to be pinned or fixed, and they're placed typically outside the extent of the section, and that will ensure column stability during erection stages, where single columns may not be tied back to temporary or permanent bracing. And then it's also worth considering that uplift might also be considered during construction. The offset is around 100 mil around the column, and we want the thickness of the base plate generally to be thicker than the thickness of the column flange. And if I turn on my x-ray there, we can see that location tubes with voids are used to allow for adjustment of the holding down bolts, which are then filled with grout at least equal in strength to the foundation. And bedding is usually between 25 and 50 mil, allowing for adjustments, and is pumped in typically via a hole in the base plate, which is not actually shown there. But stiffeners can be used alongside thinner base plates, but although they're rarely more economical than just using a thicker base plate, as they require additional fabrication. Just considering the load transfer, the column, an axial force of the column transfers the axial force directly to the base plate, or depending on what you specify, whether it's a bearing or non-loaded bearing type, sometimes to the actual welds. And then the base plate should be large enough to spread the design load through the bedding material and go out onto the foundation, into the ground. Horizontal forces, the column, again, it's typical welded, so although there's no actual strict consensus on how the horizontal forces are transferred from the base plate to the foundation, it's through a combination of both the bolts and the friction from the bedding grout. And we'll go on X-ray here again. We can use shear keys to, we can specify shear keys in the software. We can use a plate, an angle, or stub section welded to the bottom of the base plate to transfer the horizontal load into the foundation if there isn't enough capacity in the bolts and friction there. Some other notes: the design for simple moment base plates are effectively the same in the software, so you just have to input a moment value. So they're not two different connection types. And we're going to look at brace type connections as well, which will consider additional shear and potential uplift onto the base plates whenever we're looking at our brace connections. And moving on to the bracing, some general bracing information. For the arrangement of bracing, typically we aim for the centroids to all match up. So in the master frame model, we want to make sure we're noted in at the same point. But for busy connections, this can be difficult. This is quite a busy connection here, but I don't think we're limited. This is all, there's a common centroid here. But if we do offset any of these, we need to ensure that any eccentricities are accounted for locally on the connected beams or columns. And this can be done manually. And generally, the resultant moments will be calculated and provided within the connection calculation output on the software. So you might need to take some of those loads if they're significant and reassess them then independently in MasterFrame. So when specifying bracing, in many cases, they are the first elements to be erected to get the structure as stable as soon as possible. Hence, speed and convenience are often key. Some of the most common connection types, which are simple to fabricate and economical, would be our single angle bracing with welded gusset plates to back to the beams or columns, and then just in general bolted side connections. Hollow section bracing is also popular, as we can see in the bottom middle here, as it is effective in both tension and compression, but it does require an additional connection at the ends to connect to the plates, either through a T plate, an L plate, or an embedded plate, and also a cap there is usually specified for your hollow sections. There's quite a few combinations of connections arrangement for brace connections. So bracing members that can be specified, for example, are typically hollow sections, angles, channels, or flats, and can be doubled up back to back when you're looking at angles, channels, and flats. Bracing member to gusset plate connections can be directly bolted in the case of angles and flats and channels as well, but hollow sections will need that additional connection. And finally, the gusset plate itself, which is preferably pre-welded to the beam and or column. So in this connection, we're looking at the vertical bracing to beam flange. That allows for up to 6 braces into the beam flange, so 3 at the top and 3 at the bottom. The horizontal beam can be a hollow section in this case, although we have a UB shown, and because we can just weld the gusset plate direct onto the flanges, or else just the outer face of the hollow section. We can specify a vertical column here in the middle of each gusset plate, including a hollow section, but we need to understand the implications of this type of connection and how different elements are designed in the software, which I will cover more further in the presentation. So our next connection type will be our horizontal bracing to beam web. So that's similar to the previous bracing to beam connection, except the bracing is on plan. And so this is suitable for plan bracing for floors and roofs. Again, we can have up to 6 braces here, but we have we can also rotate the beam 90 degrees to allow for connection into the beam flange or web. Again, we can use hollow sections here as the gusset will be directly welded onto the outer face. So this connection type only allows for bracing elements to be connected, and in this case, anyway, gravity loads are typically carried by purlins onto the rafters anyway, so you shouldn't need to worry about having to attach a beam to that. Then we will now look at our vertical bracing to a column web or flange. So here we can see two similar vertical bracing to column connection, or K-type, K-brace type connections to the column web and the flange. The actual design output in the connection brief is limited to the bracing elements. So if I highlight this, we can see it's going to be the bracing elements, the gusset plates and the welds. And then we can see on the left-hand connection, the gusset plate is welded to the extended end plate of the beam to the column flange. But when we are designing the flexible end plate simple connection, we won't actually be considering any bolts above or below the beam flanges, so we can keep the connection simple. So when we're designing the flexible end plate in these examples, MasterSeries can give us the option to link the resultant forces from this connection or bracing connection back to our beam and plate connection. So I do have MasterSeries open here. I just need to navigate to the right connection. So if I go to, let me see where I'm at, 3. So we're on this connection here in the software. We can set that up. We can give it our loads. If it's linked to master frame, it'll automatically take all that into account. But then whenever we go to design our end plate, then if we go back and navigate to, let's just go to our, let me see, next. If we're going to our typical sort of thin plate connection, we have the option here to link the connection to the bracing connection. So we can say yes, and then we can specify where it is getting its forces from and from the braces. So just a quick reference to the software there. I'll get back to the model here. Again, we can have the usual variations of brace types here, as mentioned previously. So whether it's the different bracing elements, whether it's a connection back or so next connection type, we're going to go down to our bracing to baseplate. We can connect to the web or flange here. So again, this connection design is only concerned with designing the bracing connections. So those highlighted here now, that'll be the bracing connections, the gussets and the welds. The column base plate is designed independently, taking into account all the shear and axial forces in combination to design the arrangement and the holding down bolts, etc., that we covered earlier. So we've no requirement to physically link this or manually link this back to the column like we did in the previous example. So the gusset plate and these connections can be welded to the column only. So on the left here, or both the column and the base plate, as we can see in the web connection there. The base plate bracing can be designed in one direction at a time for either the web or the flanges. So in this case, in the MasterSeries, we will need 2 briefs or 3 if you're including the base plate. And on the left, you can see a knuckle type gusset brace there, but many different styles can be used for these gusset plates, and you can specify straight, tapered, square, or triangle as well. Now on to some moment connections. Moment connections generally are typically more expensive to fabricate than simple shear connections, although the additional material and components is not significant. It's largely due to the fabrication and the large amount of welding involved. Again, I'm using examples here for a portal frame, but they can be used in any steel structure as long as they fit the criteria. So first up is a beam-to-beam end plate connection, for example, being used in an apex here, as we're looking at a portal frame. So that connects the left and right portal and allows for the transfer of moment between the rafters using bolted end plates. We can utilize the use of specifying extended end plates here and haunch sections cut from the same section as the rafters to increase moment capacity of the section, although in many cases the haunch is only used to facilitate a bolted connection. The end plates and haunch are normally shop welded before they arrive in site and then bolted, and they allow for the design allows for major axis bending and shear, plus axial forces are all considered in the design of these bolted end plate connections. Minor axis bending and shear are not considered in this design. In an apex connection, typically we have a restraint about the minor axis at the ridge here. Anyway, so we can specify also square and rectangular hollow sections for moment connections now, but we're unable to input haunch sections in the software when hollow sections are specified. And we can also do beam-to-beam splice connections. So the Green Book doesn't give us a method to determine how minor axis bending and shear force are distributed using the previous end plate splices and bolts. So minor axis shear and bending can be managed by the inclusion of bolted cover plates for the top and bottom flange plates and also the beam welds there. These splices are often referred to as bolted cover plate splices, and they're stiffer than end plate splices, but they require high strength friction grip bolts or close tolerance holes. It's recommended to plan and locate these splices at locations of minimum bending to reduce applied forces on the splice connection, and if possible, they should be positioned close to the points of lateral restraint. And where this is not possible, account needs to be taken for potential second order effects on top of the standard frame analysis values. So I'm going to pull up another technical note here, not by us, it's an advisory desk note, and that gives you guidance for, in this case, and where is it? Unrestrained beam subjected to bending moments, but also other splice types. So these, you can work out these values and then put them into the software, and I'll just pull up the software again to show you where that can be done. Next. So if we go on to our let me see next. Yep, so our splice connections, we can work out our internal moments and then apply them to the connection there if they are required. Our next up is, well, we've got web plates, and we can also specify end plates there as well, I should note. Next up, we've got our beam to column flange via the end plate. So Portalised haunches are defined as beam to column flange by end plate connections, which we're looking at, and a Portalised rafter is designed in much the same way that other beam to column flange end plate connections are defined, except we can see a slope on both sides with extended end plates and haunches. Haunches and portals in particular carry very large bending moments and can experience reversal as well, so it's worth considering this in your connection design. The haunches, again, are commonly cut from the same section as the rafter and welded to the underside of the rafter, typically generally around 10% of the length of the span in portals. So we have the option to add many different types of beam and column web stiffeners, but for economy, connections should be arranged to avoid incorporating stiffeners. Some suggestions to avoid this include making the haunch deeper, which increases your lever arms, extending the ease connection above the top flange of the rafter, so incorporating an additional bolt row there, or adding bolt rows in general, or selecting a stronger column section. But unfortunately, those are tips, but they're no hard and fast rules, and you just have to take it each connection at a time. So for last connection type, we've got column to beam, which can be above and or below beams. So the column to beam connection is intended for use to design connections where the column is interrupted by a continuous beam. This connection can also be used to design a beam over column cap plate type connection, or for a column supported by a beam. It's based on the eaves type moment connection, similar to our previous example, and so it's subject to the same rules and restrictions for an eaves connection as presented in the SCA Green Book. And hollow sections, they're a new addition to MasterSeries 2023, and I've shown some examples here, and you can use your imagination to think where they could be used. We've also column splices for both I section and hollow sections, which can be designed within the software. We won't get time to cover that today, but if you do have any questions on any of these connections, do mention in the chat or give us a shout. I'm going to finally, just in the last slide, is just about sustainability, because it's about push in the industry, and it's now been incorporated into the iStruct exam recently as well, to start considering these topics. So what can we do in relation to sustainable designs within connections? If you guys have some suggestions, it would be great to hear them as well, because I had to do a little bit of digging there. So currently MasterSeries LCA accounts for a percentage of 5% of the overall steel frame. So it's relatively minor. But there's some tips that I have found is that, well, specifying Green Book connections are recommended to allow steelwork contractors. They've already got their workshops equipped for these types of standard connections, so it allows for more efficient fabrication. And then as well on site, it's more straightforward to erect, and it's faster and safer for workers familiar with the standard connections. Using bolted connections over welded means that the connections are demountable and can be easily reused or recycled. And then on a side note, standard bolts are preferred over high strength friction grip bolts, which are not reusable. And then some other tips, using fillet welds over full penetration butt welds if adequate, specifying tying forces to be accounted for within concrete floors, if applicable, to carry tie force back to the steel frame. Just a general note, and good record keeping for assessing increased loads in future. Whenever you're modeling your frame, input realistic design assumptions in relation to member end releases and fixity conditions. And we've got maybe an unpopular one here, but the iStruct have suggested sharing of design models between engineers and connections designers to avoid over rationalizing and over designing of connections across practices. And if you are providing connection loads as well, it's recommended to just provide the loads and then let the fabricator rationalize at a later stage with the engineer's agreement if necessary. So in conclusion, we have to be realistic. It'll be difficult to justify saving carbon emissions on connections where associated costs are so high. So if we're saving a percent or two at the cost of an increase in cost, we'll have to really dig into that. So cost will obviously play a huge factor on these decisions, but there are many other ways to reduce your carbon emissions on your building, which are also correlated with reduced costs. So I would recommend keeping up to date with guidance from the iStruct, and you can always download a trial of the MasterSeries LCA, which can help contribute to much larger savings on carbon emissions than just saving on that 5% there. So I'll hand you back to Andras there. So thanks for your time, everyone, and see you in the next one.
Okay, thank you, Patrick. Okay, so I'm gonna start designing a steel connection from scratch to show you how easy it is to work with the MasterSeries connection design module. So programs and connections. And I'm gonna take a brand new file, webinar. Wait, yeah, and create. Okay, I'm gonna accept all the default facilities, default well size, clearances, etc. So this is our joint template library. So here you can select the joint type you want to work with. So we have moment connections, simple connections, and we have the bracing connections. And under each category, you can find several templates of connections. You only need to do is to select the closest match to your desired connection configuration. So for example, if you want to design a double-sided valley connection, click on the proper template and the module will create a nice initial connection model you can start working with. Now I'm gonna select the default eaves connection template to present how a connection can be built up from scratch. But after we design the connection, I will return and speak a bit more about the joint template library and how you can use it to standardize your design workflow. So select default. Okay, so this is the user interface of the connection design module. It's pretty simple. In the middle of the screen, we can see the interactive graphical area showing the created default beam to column connection. On the right hand side is the property tree, which includes all the elements we can manipulate or use in the connection type we choose. So for example, we can change the beam cross section, add more bolt rows or stiffeners if needed. And as I said, the graphic is interactive, meaning if you click on any components on the graphic, it will immediately redirect you to the proper part of the property tree. So for example, let's click on the end plate and here it is. On the left hand side is the default calculation. We have a warning as we haven't applied any loadings yet, and the calculation requires apply loadings. If you have any problems with the calculation, the program gives you a warning message in the line of the failing design check and turns the background from white to cyan blue. The program not only checks the design rules, but the detailing rules as well. So in case of any detailing issues, the background of the graphical area turns into cyan blue, and the check dimension screen gives you a detailed description of the problems, but it's empty now. Good. Let's look at the toolbar, the main menu. With the toolbar, you can add further joints to the file, so it is not necessary to create new file for each connections. You can change the graphical visualizations. You can run checks on the current connection or on the whole file. You can do auto design, and of course, you can send out your report to a physical printer, save it as a PDF file, or export it to Microsoft Word. The main menu contains the usual file menus. Under the options, you can change your design code, the program design to the Eurocode and to the old British standard. Okay, so let's apply some forces to the joint, beam forces. I'm going to apply 450 kilonewton meter as a beam moment. A positive moment opens the top of the joint, meaning it is an anti-clockwise moment. The tooltip area here below the property tree gives you information about the input value. And as you can see, once we apply the moment, the program automatically refresh the detailed calculation, and now we have results. So let's apply 150 kilonewton as shear and 100 kilonewton as an axial force. Positive shear force is downward, and positive axial force is compression. Okay, so here we can clearly see that the connection is failing. In the summary of the result, we have a warning in the line of the moment capacity, and it says that the connection is more than 5 times overstressed. And if you scroll down in the detailed design, we will see that the failing component is the bolt row in the bolt row in tension, but this is also shown on the graphic, indicated by this small red square placed over the failing bolt row. The MasterSeries connection design uses the component method to calculate the connection resistance, meaning it defines the weakest compression and tension components and using their resistance to calculate the overall resistance of the connection. Meaning, if you want to strengthen the connections, we have to strengthen the weakest component, which is, as I said, the top bolt row now. So let's see the options on how we can strengthen the bolt row. For example, we can increase the material grade 10.9, or we can use a bigger bolt, 22 mil. However, these do not help a lot. Rather than do any of these, we can significantly increase the moment capacity of the connection by extending the lever arm between the top bolt row and the compression zone. To do this, I'm gonna add a hunch to the beam. So I click on the beam, and under the beam properties, we can define a hunch. Okay, so let's say the hunch length is 2,500 mil, and the overall hunch depth, which is the height of the beam plus the height of the hunch cross section, is 900 mil. The cross section from which the hunch is made can be taken to be for the beam, or alternatively the hunch can be cut from a different cross section. Okay, so the calculation has been updated. We can see that the moment capacity of the connection is much higher. However, it is still not enough. It is still more than 2 times overstressed, and the failing component is still the top bolt row. Before we manipulate the bolt rows, let's go back to the beam properties and apply a 5-degree slope to have a more realistic design. Okay, so let's see the bolt rows. Top bolt row is the failing component. To increase the resistance of this component, we have to go to the bolt rows property. Yes, upper bolt rows, and add a second bolt row. I'm going to use the same 80 mil gap. Okay, by using a second bolt row in the tension zone, the connection utilization ratio went down to 1.5. But in this case, we have a new weakest component, which is the column web in compression, shown by this symbol. To add further strength to the connection, now instead of adding more bolt rows, we have to strengthen the column web. Of course, we can do this by using a bigger column cross section, but adding a column stiffener is a more economical way to do this. So under the main stiffeners, I'm going to select bottom stiffener, and by typing 10 mil to the thickness, we can add a bottom stiffener. Okay, and as you can see, the weakest component is again the bolt rows in tension, and the connection is still filling. Okay, let's go back to the bolt rows and add the necessary bolt rows to make the connection work. Adding a third bolt row is still not enough. 6 times overstressed. Let's add a fourth bolt row. Okay, the moment capacity of the connection looks good now. However, the weld of the bottom stiffener is failing, so we have to return to the bottom stiffener properties and set the weld size to 10 mil. Okay, and now the connection works, passes all the design checks. The detailed result has a white background, which means we have no warnings. Okay, but of course there is no connection with only one load case. What I'm gonna do is to add an additional load case to see how we can handle multiple load cases. To do this, we have to click on this big plus icon on the top toolbar. Okay, a second load case has been added, so now we can go and apply the beam loads to it. The beam moment is 250 kilonewton meter, which is an uplift, a clockwise moment. The beam shear minus 50, which is an upward loading, and the axial force is minus 100 kilonewton, which is a tension. Okay, let's click again on the add button and add a third load case and apply minus 350 kilonewton meter as beam moment, minus 100 kilonewton as shear, and minus 200 and axial force. So now we have 3 load cases. Here we can switch between the applied load cases. Load case 1 looks good, connection works. Load case 2 is good. However, in the load case 3, the connection is failing. And as we can see, the weakest component is the column web in compression. So we have to, but because the moment is a reversal moment, in this case the compressed column web is the top of the column. So let's strengthen the column web by adding a top main stiffener. Okay. So it's still filling, and again the failing component is the bolt rows in tension. However, because this is a clockwise moment, that's why the bottom bolt rows are in tension. So to strengthen the bolt rows, now we have to add a second bolt rows, a second lower bolt rows. Yeah, and now the connection works, and there is no further failure. Using the brief failure checks, we can we can ask the program to quickly check to see if there are any failing load case in the connection. But now it's all good. Okay, so this is how we could manually optimize steel connection. But of course, in the MasterSeries, we can ask the program to do this automatically. So let's hit the reset button first to reset the connection back to the default. Yeah, except for the hunch and then the sloping. And now we can click on the auto design. There are only a few parameters we have to set. So let's use the same 80 mil bolt row distance and 10 mil stiffener thickness. And of course, we want to run the auto design for all the locations. So I will leave this button on. Okay, and by clicking on the auto design, we can quickly auto design the connection. And it's ready now. The program, the auto design function runs through all the cases and optimize the connection, and the result looks the same as we got before. Okay, so this is the process of the connection optimization. Now I would like to return to the joint template library and speak a bit about how you can use it to optimize and standardize the design workflow. Okay, so back to the joint library. As I already mentioned, we can use the built-in joint templates as a starter for our connections, and then you only need to modify the necessary parts. Joint template library has a search option, or you can use the text to filter the connections as well. However, the joint template library can also be used for an effective and standardized design workflow for your connection design. In the MasterSeries, you can create your own company or project templates to avoid the usual mess when your engineer uses the full range of plates and bolts, etc. in a single project. With these, you can reduce your delivery time and cut the total construction time too. So you can save any connection design as a template and reuse it again. So for example, if you want to use this connection as a template, under the utilities, you have an option to save joint as a template. We can give a name, beam to column, left. Yeah, we can add text as well. So let's say it's bolted, hinged, and we can create a thumbnail as well. So with this little tool, we can create a nice screenshot. And that's it. And save. And the new custom joint templates will be available under the user library. So if we switch over to the user, then here it is. So this is the recently created joint template. And of course, the joint template library is shareable. So the joint template file is stored on this file path. So you can share this file with your colleague or store it on a shared network location. And with this changed database file, you can load in another joint template database file. Okay. Before I finish the webinar, I would like to quickly run through the latest enhancement in the connection design module. Of course, we made several improvements and enhancements to the connection module in the recent years. Now I'm going to highlight only the major improvements. Patrick already mentioned some of them during the introduction, but now I would like to quickly show them inside the program. Okay, so let's start with the baseplate connection and the implemented Eurocode anchor bolt calculation. So under the baseplate, yeah, I'm just selecting this baseplate connection. So the implemented Eurocode 19924 anchor bolts calculation can handle concrete edge conditions. So in the property under the concrete property, so now we have the option to specify the concrete edge distance, and then the program can properly calculate the pullout for constraint edges, concrete edge shear, bolt shear with lever arms, and of course, if you have to improve your concrete edge shear, there is an option to specify size steel as well. Okay. The next improvement I want to highlight is the hollow section beam. Is the hollow section beam in the beam to column moment connection. So yeah, this one. So in the MasterSeries 2023, the beam to column moment connection supports SHS or RHS hollow section beams as well. So this is a nice example of it. Similar to the beam to column connection, column to beam moment connection also supports hollow sections. Oops. So the column cross section can be a rectangular hollow section. So yeah, under the column section, now we have the option to select to use an SHS and RHS. Yeah. Okay, and the last improvements or the last new features I want to highlight is the beam-to-beam flexible end plate connection, the top plate option. So simple connection, flexible end plate beam-to-beam. So we received several user requests to implement a new connection type, having a flange top plate on the outside face of the supported beam to connect the connecting beam with a flexible end plate. So in the MasterSeries 2023, this option is available now. So as a part of the beam-to-beam flexible end plate connection, you can now simply turn on the top plate option. So this is this flange top plate is an option under the connecting beam properties. So if you turn this off, then it goes back to the normal film plate, flexible end plate option, but using the top plate, it looks better. Okay. So ladies and gentlemen, I would like to thank everyone to attending today. I hope you enjoyed and learned in this webinar, and see you on our next webinar. If you have any further questions, you can get in touch with us on our usual channels. If you want to try out the software, just go to the MasterSeries website and fill in the request form to do so. After the webinar, please do not forget to fill in the short 1-minute survey to let us know how you like the webinar. So ladies and gentlemen, again, thank you very much for attending, and have a great day.